Hello everyone. Today we'll be studying few more properties of random variables. So let me begin with some simple properties. So let x1 and x2 be random variables. Then can we say that if we define y1 as a maximum of x1 x2, or if we define y2 as a minimum of x1 x2, what can we say about y1 or y2? So can we say that y1 y2 are also random variable? Okay, let us try to check. What is our definition of random variable? We say that a function is a random variable if inverse image of every Borel set under that function is belonging to the original sigma field. Okay, so we will say that x1 is a random variable, suppose defined from omega script a to r script b, and we say that x1 is a random variable if x1 inverse script b is actually subset of script a, right? Inverse image of every Borel set should be in script a. So inverse image of the entire Borel sigma field should be subset of script a. Same thing is true for x2. x2 inverse of b should be in script a. Of course, we have defined x1 and x2 on the same sigma field. Otherwise, we can't take their maximum, minimum, etc. And now what we want to prove is y1 inverse of script b should also be subset of a, and y2 inverse of script b should also be subset of a. This is what we want to prove. Okay. So let us try to think. So what we have to actually do is we have to start with some arbitrary Borel set, take its inverse image and prove that that inverse image is in script A. And if we can prove it for arbitrary Borel set, then we can say that yes, it is true for every Borel set and hence for the entire Borel sigma field. However, this seems a bit difficult to do. Hence, we are going to use the economical definition of random variable. Do you remember what was the economical definition? Economical definition stated that you don't have to worry about proving it for every Borel set. You can just prove it for a subset of Borel sigma field, but it should be that subset which can generate entire Borel sigma field. For example, it can be any class of intervals. So for example, it can be say intervals of the type minus infinity to x, where x is in R. Okay, we know that sigma of C1 is script B. Hence, if we can prove that inverse image of every set in C1 is in script A, then we can conclude that inverse image of every Borel set is also in script A. This is what economical definition of random variable says. Okay. So let us try to prove that. So what we want to prove is inverse image. So let me do for y1. So y1 inverse of say minus infinity to a. Okay, I am consciously taking a and not x because I don't want you to get confused between x and x1. This x is actually any real number, so I am taking a. So we want to prove that y1 inverse of minus infinity to a is a Borel set. Okay, so let me write down. So what would be y1 inverse of minus infinity to a? It would be set of all omegas such that y1 of omega is in minus infinity to a, correct? This is the definition of inverse image. It is set of all omega such that y1 of omega is in minus infinity to a. Now y1 is in minus infinity to a. It means that maximum of x1 omega to x2 omega is in minus infinity to a. Okay. Now maximum is in minus infinity to a. It basically means that maximum of x1 omega and x2 omega is less than or equal to a. It is in this interval, means it is less than or equal to a. Okay. If maximum is less than a, it means that both of them have to be less than or equal to a. So this is same as saying that it is collection of all those omegas for which x1 omega is less than or equal to a and x2 omega is also less than or equal to a. Both should happen. Okay. So it is collection of all those omegas for which x1 omega is less than or equal to a intersected with collection of all those omegas for which x2 omega is less than or equal to a. Correct? Both the things should happen. So we are taking intersection. And what do I know about these two sets? Now the first set is actually x1 inverse of minus infinity to a. And second set is x2 inverse of minus infinity to a. Okay. And we know that x1 and x2 are random variables. So we know that this belongs to script a. This belongs to script a. And script a is a sigma field. So intersection of any two sets from script a must be in script a. And this is what we wanted to prove. Okay. So we have proved that if x1 and x2 are two random variables, then their maximum is also a random variable. Okay. Can you prove something similar for minimum? Just think. I'm sure you would be able to do that. Okay. So let me list homework for you. So your first homework is do the same thing for minimum. So prove that y2 is a random variable with respect to same sigma field. Next homework is generalize this to n. So if you define y1 as maximum of x1, x2, xn and y2 as minimum of x1, x2, xn, then prove that this holds, means y1, y2 are random variables. Okay. You just have to use the property. For example, in maximum of x1, x2, xn, instead of getting intersection of two sets, you will get intersection of n sets. But we know that sigma fields are closed under finite intersection. So it would work. Okay. Next step is actually generalize it to infinite case. So in infinite case, we don't call things minimum and maximum. We call them infimum and supremum. So let me state the result. So let x1, x2, etc. be a collection of random variables. Okay. And it is actually a countable collection. Okay. It's not a finite collection. It's a countable collection of random variables. Okay. And let y1 be defined as supremum over this, supremum over x1, x2, etc. and y2 be defined as infimum over x1, x2, etc. Then our job is to prove that y1 and y2 are random variables. Okay. I hope you have noticed that when I am taking minimum maximum, I have to fix omega and then take minimum maximum, etc. Okay. Just to give you a feel, let me give you some example. Suppose x1 is defined as number of heads. Okay, suppose I am tossing 2 coins. That is my experiment. x1 is defined as number of heads and x2 is defined as, say, number of tails. Then what I know is x1 of HH is 2, x2 of HH is 0, x1 of HT is 1 x2 of ht is also 1, x1 of th is 1, x2 of th is also 1, x1 of tt is 0 and x2 of tt is 0. So for different omega, my x1 x2 are different. So if I want to define y1 as maximum, I have to take for each omega. So y1 of hh would be defined as 2 because it is maximum of this 2 and is 0. Then y1 of ht would be defined as 1 because it is maximum of this 1 and this 1. Similarly, y1 of th would be defined as 1 and y1 of tt would be defined as 2. Getting? So y is again a random variable. So for every omega it takes different value, and for every omega it takes maximum of x1 x2 for that particular omega. Okay, and the same thing we are generalizing now to a countable collection. So I have x1 x2 dot 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 is a collection of random variables, countable collection. You can also call it a sequence because countable collection is a sequence. And now we are defining y1 and y2 as supremum and infimum. So this time let me do for infimum, supremum can be homework. Okay. Now for y2, let us consider another type of interval. Okay. Because our economical definition says that we can prove it for any one type of interval and we are done. So let me consider y2 inverse of open A to infinity. Okay. So this is collection of all those omegas for which y2 omega belongs to open A to infinity. y2 omega belongs to open A to infinity means this is collection of all those omegas for which y2 omega is strictly greater than A. Okay. So this means this is collection of all those omegas for which infimum of x1, x2, etc. is strictly greater than A. Okay. So let us draw picture. So A is somewhere here and we are saying that infimum is to the right of A. So of course all the yi's also have to the right of A, because if that is not true, means if say one yi is here to the left of A or equal to A, then infimum would be equal to that yi. So infimum would be either less than A or equal to A. Correct? So this is same as saying that xi is greater than A for every I. Okay so far? So we can say that this is intersection over n going from 1 to infinity set of all omegas such that xn of omega is greater than A. Okay? Everyone with me so far? What we know is each xn is a random variable. So this is inverse. Okay, let me write down. So this is actually integral over n going from 1 to infinity set of all omega such that xn omega belongs to A to infinity. So this is same as saying it is intersection over 1 n going from 1 to infinity of xn inverse of A to infinity. Now since xn is a random variable for every n, each of these sets belongs to script A, and since script A is a sigma field, countable intersection of sets inside script A is also in script A. Okay, therefore y2 is a random variable. Okay, now your homework is to prove for y1. Okay, so homework is prove that y1 is a random variable. Okay, so these are two we have proved maximum and minimum are random variables. Now we are going to introduce different types of random variables. So let me start with the simplest type, which is known as simple random variable. But before that, let us revise what is meant by partition of a set. Okay, so we say that, say B1, okay, let me use some other notation. We say that A1, A2, AK is a partition of some set omega, if and only if AI intersection AJ is equal to phi for every I not equal to j, that is the sets are mutually disjoint, pairwise disjoint, and actually they should be mutually disjoint also, not just pairwise. A I union over I going from 1 to k should be entire omega. That is, they should be mutually exclusive and exhaustive. Is it okay? This is how we define a partition. Let me take a quick example. For example, if I consider a set of real numbers, then q and q complement. So basically I can write q complement as a partition because they don't have anything in common. You can't have a number which is both rational and irrational, and their union gives me entire R. Okay. Or if I am talking about set of natural numbers, then even natural numbers and odd natural numbers, they form a partition. Okay. Also, if I am again talking about set of natural numbers, then set of prime numbers, composite numbers, and singleton one. This will again be a partition because one is neither prime nor composite, so we'll keep it separate, and prime and composite. So I have three sets now which form a partition. Okay, everyone clear with the definition of a partition? If yes, then let us move ahead. So we are now going to define something called as simple random variable. Okay, so simple random variable. How do I define a simple random variable? So let omega script A be a measurable space. Let A1, A2, AK be a finite partition of omega. Okay, A1, A2, AK be a finite partition of omega. What do we mean by finite partition? The number of sets in that partition should be finite. So here number of sets is k. So k is finite. Okay. Individual sets may be infinite. For example, I know that set of all prime numbers is an infinite set, or set of all composite numbers is an infinite set. Still, I would say this is a finite partition because it contains only 3 sets. Okay. So this is important. So A1, A2, AK be a finite partition of omega, and let x be a random variable defined from omega A to RB. Okay, so we say that x is a random variable, x is a simple random variable, I'm sorry. We say that x is a simple random variable if and only if x can be expressed as sum over I going from 1 to k, small ai indicator of capital AI. Okay, it may look like a slightly complicated form, but just try to understand, it's very simple. Let me draw a picture. So suppose this is my entire omega. We first define the partition. So suppose this is the partition. So I have A1, A2, A3, A4, A5. Okay. Now let me say that on this entire part A1, x takes value small a1. On this entire part A2, x takes value small a2 and so on. So what we have defined is x of omega is equal to small ai for every omega in capital AI. Okay. X of omega is defined as small ai for every ai in capital A. For every omega in capital AI. So x takes only k possible values. Okay. So the set of possible values of x is assuming they are all distinct. Okay. So x has at most k distinct values. Then we say x is a simple random variable. Okay. And that k distinct values part is actually expressed by our diagram here. So capital A1 kind of becomes the set of all those omegas for which x is defined as small a1. Okay, that is exactly what has been expressed in this notation. So indicator function would take values 1 or 0. So indicator of omega is 1 if omega is in AI. So at that time, if it is in AI, it cannot be in any other AJ. Okay, for example, if suppose omega is in A1, because AI's form a partition, it cannot be in A2, A3, etc. So all those indicators would be 0 and will be left only with A1 into indicator A1. So it is same as A1. Is it okay? Same story we can check for other AIs. So basically capital AI is defined as collection of all those omegas for which x value is small a. Okay. So in such cases means if the number of possible values of a random variable is finite, then we say that x is a simple random variable. Clear to everyone? What is meant by a simple random variable? Okay. In elementary random variable, we just extend it to countable partitions. Okay. So let me write down for the sake of completeness. It's very easy, but let me write down. So we now define elementary random variable. So we consider a countable partition. So let A1, A2 dot be a countable partition of omega So we define x as sum over n greater than or equal to 1. Now my sum is countably infinite, it's not finite, as an into indicator of an omega. Okay. So again on each set in the partition it takes one value and set of possible values is countable. Just to give you some easy examples. Bernoulli is a simple random variable. Binomial is also a simple random variable because the set of possible values is finite. Whereas Poisson becomes elementary random variable because set of possible values is countably infinite. Is it okay? So this is simple and countable, elementary random variable. Now today we'll stop here. We'll continue and study few more properties of simple random variable in the next lecture. Okay, thank you.